I'm now going to give the solutions to the linear algebra portion of the diagnostic quiz. So onwards to question 7. The key concept for this question is eigenvalues and eigenvectors, and the same for the next question. So this is the following. We have a 2 by 2 matrix A, which is given as 3, 4, 4, 9. We're also given a vector V, which is 1, 2. And it asks, is V an eigenvector of the matrix A? So let's remember in general what is an eigenvector. So V is an eigenvector of A if, when I multiply A times V, I get back a scalar multiple, often denoted by lambda, times V. Okay, so just to be clear here, this is a matrix, this is a vector, and this is the same vector, whereas this is a scalar, or just a number. Okay, so all we need to do is just plug in A and V into this and plug in the numbers above and just see if such a relationship holds. So this will also refresh our memory as to matrix vector multiplication. So 3, 4, 4, 9 times 1, 2. Remember how matrix multiplication works. Right? We go this way and this way. Okay, so let's write that out carefully and see what these numbers are. So this is equal to 3 times 1 plus 4 times 2. Okay, so that's 3 times 1 is 3, plus 4 times 2 is 8. And then on the bottom row, I have 4 times 1 plus 9 times 2. Which gives me 4 times 1 plus 9 times 2. Doing this addition, this is equal to 11, 22. Okay, so for this to be, for the answer to be affirmative, that this is, that V is an eigenvector, 11, 22 needs to be a multiple of 1, 2, and we see that in fact it is. This is 11 times the original vector, 1, 2. So the answer is that indeed V is an eigenvector of A. And we've also answered the next question, which asks what's the eigenvalue, and the eigenvalue of V is 11. Okay, so that's it for eigenvectors and eigenvalues. And again, the key thing here is to also remember, refresh our minds for matrix vector multiplication. And we need this in the next question. Okay, so question 9 was about MOOCs. Question 10 asks, find the dot product of the two vectors, v1 is equal to 1, 2, 3, and v2 is equal to 0, 2, 0. So the dot product of v1 and v2 is also sometimes written as v1 transpose v2, and then we can think about v1 transpose as a matrix and v2 as a matrix and use our matrix multiplication rule. So writing it out this way, we see that this is equal to v1 transpose. v1 is a column vector. v1 transpose is therefore a row vector, 1, 2, 3. v2 doesn't have a transpose, so I'm going to write it as a column vector, 0, 2, 0. And again, if I do my rule for matrix, this is just a 1 by 3 matrix, and this is a 3 by 1 matrix. So I do my matrix multiplication, just like we did before, and we get that this is equal to 1 times 0 plus 2 times 2 plus 3 times 0. or in other words, 4. And this is the answer. Okay, so in general, if I have a vector x, which is x1, x2, xn, and a vector y, y1, y2, yn, then the dot product of x with y, which is the same as x transpose y, and by the way, sometimes you'll also see notation, this bracket notation, x comma y, it's equal to x1, y1 plus x2, y2 plus xn, yn, or using summation notation, the sum from I equals 1 to n of xi times yi. But the answer to this question is, again, just 4. Okay, the next question asks us to understand projection. This is the key concept here. And it says v1 is the vector 1, 2, and v2 is the vector 1, 1, and it asks us to consider what is the projection of v1 onto v2. So let's look at a simpler example of this before I just tell you what the answer is. So a more simple is, let's say, I'll write different letters so we don't get confused. W1 equals 2, 3, and W2 is equal to 1, 0. So now we can draw these. So I'm going to draw the x-axis, the y-axis, and the x-axis. 1, 2, 3, 4. 1, 2, 3, 4. Oops. So this, maybe I'll choose a different color since I can do that. So this is W2, and 1, 2, 1, 2, 3. This vector is W1. So what's the projection? Well, you can see here that the projection of W1 onto W2 is basically just the shadow, onto this axis. So in other words, the projection, this is the projection or shadow of W1 onto W2. Okay, so now we're using our visual intuition here to solve this problem. So the projection is the vector 2, 0. Okay, so this is now suggestive. We want to convert this intuition into a general technique for calculating. One of the beauties of the formalism of linear algebra is that we can use our intuition in 1, 2, and 3 dimensions where we can visualize things and then extend it to higher dimensions where there's really no need or ability to visualize things. So an observation here is that what I've done here is that the projection of W1 onto W2, one way I can write it is W1 transpose W2. This is now a scalar. This is the length of the projection, and it's in the direction of W2. So let's do this out. So this is equal to, using our work from above, W1 transpose is, I'm going to write the transpose of the column vector as a row vector, 2, 3 times 1, 0. And you can see that this is now a scalar times the vector 1, 0. So this is 2 times the vector 1, 0, which is equal to 2, 0, which exactly agrees with this picture above. Something else I want us to note, however, is let's now suppose that W2 were twice as long, or 3 times as long, or 4 times as long. The shadow shouldn't really depend on the length of W2. So the key point here is that the projection of W1 onto W2 should not depend on the size or length or magnitude. These are all words that mean the same thing, of W2. So in fact, what we mean when we say, whoops, what happened here? When we say the projection of vector W1 onto W2, we really mean the projection of W2 onto the direction. See, direction doesn't have a notion of magnitude defined by W2. So what we need to do in order to fix this is take this formula that we derived up here and make sure that we're not factoring in the size of W2. How do we do that? We're just going to divide out by the length of W2. So the formula for projection is the dot product of W2 onto W1. This is a scalar divided by the length of W2. This is the Euclidean, sorry, I mixed up my indices here. Of course it doesn't matter, but I just want to be consistent with what I was doing above. The length of W2, I'll explain this notation in a second. Okay, so this is now a scalar, in other words, just a number. But a projection should not return a number. A projection of a vector, just like the example above, is still a direction, still has direction. So I need to multiply this by the vector W2. So this is the general formula. So we still need to define what this notation is. So I need to define my notation. I'm going to drop the W2 here. I'm just generically going to explain what this notation is for some vector x. Okay, so this is called the Euclidean length. And the reason it's called the Euclidean length is that it's the length of a vector the way that you would measure it if we were to walk out on a field and I drew the axes and drew the vector. This is how you would measure it. So in other words, if I give you any vector, if this is x, then this quantity here is exactly this length. So how do we compute that? We use the Pythagorean theorem. Remember that this is the hypotenuse of this right triangle. And in fact, we know that let me write out the coordinates of x, if x is equal to the vector x1, x2, then that exactly means that this length is x1, this length is x2, and therefore its Euclidean length is equal to x1 squared plus x2 squared square root. This is just the Pythagorean theorem. Okay, so now we have all the tools in place to actually answer the question. So back to the question. we have v1 is equal to 1, 2. v2 is equal to 1, 1. So using a formula, plugging in this formula, we get the answer that the projection of v1 onto v2, remember this means onto the direction defined by v2, is equal to, I'm going to scroll up so we won't be able to see this formula, is equal to v1 transpose v2, this is a scalar, divided by this Euclidean norm of v2 in the direction v2. So let's compute all three of these parts. v1 transpose v2 is equal to 1, 2, 1, 1, which is equal to the scalar 1 plus 2, or in other words 3. That's the first part. The denominator is this quantity. Remember that this is now defined by the square root of 1 squared plus 1 squared, or the square root of 2, and therefore we have our answer. So the projection is equal to 3 divided by square root of 2, this is a scalar, times the vector v2, which is just 1, 1. Or if you prefer to write this differently, 3 root 2 over 2 in the direction 1, 1. So this is a projection, and we've also learned in this doing this exercise what this concept is of Euclidean norm. And finally, we come to vector calculus, and there's a few more concepts we need to define here if you haven't seen them before. The vector calculus question tells us that we have a function of two variables, x and y, and it's equal to x squared plus 2y squared. And the question says, compute the Euclidean length, we just learned what that is above, of the gradient of f of xy at the point x equals 1, y equals 2. Okay, so the key thing that we need to remember here is what the gradient is. This is the key definition that we need in order to answer this. And the gradient is really just a derivative. And so if we just had a function of one variable, then the gradient of g of x is just the derivative. In other words, g prime of x, or d dx of g of x. But now we have two variables. So for f of xy, we need to compute the derivative with respect to x and the derivative with respect to y. And these aren't derivatives, they're in fact partial derivatives. So to use the notation, though it's again just the calculus rules are exactly the calculus rules you know, the derivative with respect to x is denoted like this. And it's obtained by treating y as a constant. So the derivative of our function, which remember is x squared plus 2y squared, is the derivative with respect to x of x squared, that's 2x, plus the derivative with respect to x of 2y squared, but y is a constant compared to x, so it's the derivative of a constant is 0. Okay, so it's 2x. And then we need to compute the derivative with respect to y of f of xy. So this is the partial derivative of x squared plus 2y squared. The derivative of x squared with respect to y is 0 because x is a constant as a function of y, so it's 0. Plus just the derivative of 2y squared. which is 4y. So the answer is 4y. So now we have computed the gradient of f. And I'll introduce some notation that's used. This is a symbol for gradient. So this gradient of f, of xy, is the vector. I just keep track of these two things as a vector. 2x and 4y. Okay, so we've done the first part of the problem. We've computed the gradient of f of xy, but now we need to evaluate it at the point 1, 2. So next, we evaluate the gradient of f of x, y at x equals 1, y equals 2. This just amounts to plugging in. Some more notation here that you'll sometimes see, so it's important to at least be aware of it, is this vertical line. This gradient evaluated at x equals 1, y equals 2 is 2 and 8. And now we need to compute the, and now we just need to compute the Euclidean norm of this vector 2, 8. I'm just using the formula. This is the square root of 2 squared plus 8 squared, which is the square root of 4 plus 64, or the square root of 68. And that is the end of the diagnostic quiz. So all of these concepts of dot product, eigenvector, eigenvalue, Euclidean norm, and so on are going to be repeatedly used, and very important to be not just familiar, not just aware of them, but very comfortable